Hello, everyone. So, welcome everywhere you are. Good morning, good evening. Welcome to this online workshop. My name is Wolfertstetter. I am a PhD in electrical engineering and renewable energy. I will moderate this workshop with my colleagues, Thore. So, welcome to this online workshop. Thank you very much for joining us today. We will have a great workshop today. So today we are going to talk and discuss artificial intelligence application in fault detection and maintenance strategy for photovoltaic and concentrated technologies. So let's start firstly with a demonstration of the challenge of artificial intelligence and photovoltaic in and CSP technologies. So as you know, in recent years, the adoption of solar power sources has seen significant growth worldwide as solar energy, particularly photovoltaic and CSP, continues to play a pivotal role in the transition to sustainable energy system. So it's become increasingly essential to ensure the reliability and the efficiency of solar generation technology. In parallel, fault detection maintenance strategies are crucial aspects of maintaining the performance and longevity of photovoltaic and CSP systems. Accordingly, innovative approach, best practices, emerging trend in using artificial intelligence to enhance fault detection accuracy, maximize the operation efficiency of photovoltaic and CSP system have been recently adopted. So to discuss this challenge today, this workshop will bring together a lot of learning experts in the field of artificial intelligence and solar energy. First, we will have Mr. Mohammadreza Aghaei will present about autonomous monitoring and analyze for terawatt photovoltaic transition. Then we will have Mr. Fabian Wolfertstetter with a presentation of aerial solar field inspection with Volateq software suite. Next, Mr. Marc with a presentation in the measurement of irradiance for photovoltaic and PV and CSP plants. Then we will switch to Mr. Müller for a presentation about physics-based artificial intelligence in revisioning, solar estimation, and cleaning optimization in large-scale photovoltaic. And we will close this presentation with Mr. Catlin Mattheis with a presentation on building advanced solar losses model with AI and ground level data. So it's a pleasure to have expert today with us. So first, we will start with Mohammadreza Aghaei. Mr. Mohammadreza.
Hello, can you hear me?
Yes. Thank you very much for joining us today.
Thanks a lot for invitations.
Yes.
And I'm happy, and it's a pleasure to be part of this event.
Yeah, the pleasure is for us. So a brief introduction for Mr. Mohammadreza Aghaei. Dr. Engineer Mohammadreza Aghaei is a highest accomplished professional with a PhD in electrical engineering from Politecnico di Milano, Italy, with extensive experience as a visiting scholar and postdoctoral scientist and renowned institutions such as Fraunhofer, ISE, So I say that Mr. Mohammadreza has a PhD. So Mr. Mohammadreza has extensive experience as a visiting scholar and postdoctoral scientist at renowned institutions such as Fraunhofer, ESU, Elmos in Berlin, He has made significant contribution for solar photovoltaic and sustainable energy system, serving as a guest lecturer at the University of Freiburg at holding adjacent professorship. So Dr. Aghaei has demonstrated he is committed to academic. He currently leads the UA Horizon 2020 project. So let's start with Mohammadreza. Mohammadreza, the floor is yours.
Thanks a lot for the introduction. So let me share my screen.
Okay.
Can you put me as a host?
Yeah, of course. Yes, the floor is yours now. Yeah, Mr. Mohammadreza.
Yes.
Yeah, nice.
Can you hear me well?
Yes.
Can I start? Okay, great. So very welcome to my presentation. And first of all, actually, again, I would like to thank the organizer for a very interesting event. In this talk, I'm going to present the autonomous monitoring analysis and how it aims to enhance the reliability and durability of the PV systems, and how to contribute to the terawatt photovoltaic transitions. So in this talk, actually, we are going to discuss a bit about the energy transition and the autonomous monitoring analysis and why it's important. And I will give the introduction to the failures in the PV modules, component and systems. And I introduce also the artificial intelligence technology and the application of the AI. I will give a lot of case studies and also the examples. And at the end, I will introduce to you actually the recent developed software package for the aerial inspection. We call it RoboPV. So regarding the energy transition, so as you know, actually energy transition refers to the global energy sector shift from the fossil-based systems, not only for the energy production, also for the consumption. And so we are actually smoothly try to move from the fossil-based systems to the renewable-based systems. And you can see and observe the energy production by 2050 and middle of this century. And as you can see, there are a lot of progress in the renewable side. So the movement is very clear here. So from the fossil base to renewable base, and the solar energy will be one of the pioneer energy source for this transition. And by 2050, actually, we have a lot of, we need actually much energy, and there will be a lot of demand. And this demand actually will be relied to the renewables, and only the renewables is able to manage this demand. And of course, this transition will have a lot of challenges, and that's not really easy task. And however, actually, different sectors needs to contribute in order to actually mitigate the climate change and also other emissions. So I would like also to show you this very interesting graph, and that's about the timeline of the energy transition. So you can observe here some like milestones or achievement from 2020 by 2050. So by 2020, actually, we had a 6% energy demand drop because of COVID-19. And in 22nd, for the first time, the PV installation reached to the 1 terawatt installation. By 2034, actually, is expected the maritime energy demand will be peaked. And by 2043, actually, at least the half of the world vehicles will be electrical. So that's like the statistics for the futures. And by 2042, actually, the wind will be around 30% of power supply, and solar will be around 35% power supply. And hopefully, actually, by middle of this century, we will have over 51% from the renewable side. And so, as you know, actually, the solar photovoltaics is the foremost renewable energy technology for cost-optimized climate change mitigations. And as I said, this is not easy, and we need much installation of the PV. So let's say massive PV installation, so ranging from the 20 to 75 terawatt peak by middle of this century. And by end of the century, I mean, we need around additional 100 terawatt peak. Yeah, here is also the graph of the increasing of the, showing the increasing of the installation of the photovoltaics worldwide. So as you have all actually, the installation, as I said, also for the first time in 2022, actually we reached to the 1 terawatt installation, and for the first time we passed the annual capacity over the 200 gigawatt. That was actually one of the very great milestone. And but now the question is that why actually we need the intelligence monitoring and autonomous monitoring and analysis. And this question now actually makes sense because we are in the terawatt installations era. So that's something actually we really sense it. As you can see and observe these plants, they are actually, the most largest plants around the world. Of course, we have a recent larger scale plant over 1 gigawatt installation. So the question is that if you just have a look to this plant, you see actually is needs much efforts in order to do the monitoring. And the question is that how, it's possible to monitor such a plant, and how many days required to analyze the monitoring data, and how we can actually detect the faults in all the strings, and how would be the decision making for remedial action, and how many days takes time actually to really implement the remedial action, and how also we can actually rely on the outcomes. So for sure, the traditional way don't much help. So we need to actually think about the precise, reliable monitoring methods in order to evaluate the performance of such a large scale plants. And as we are in the transition of the PV terawatt, so we need really to think the intelligence and innovative method for such a capacity. So before going to discuss about the autonomous monitoring and reliability and application of the AI for the PV monitoring, so it would be good actually to discuss a bit about the failures. So in the figure in the left side, you can observe the classification of the faults of the PV systems. So the failures are classified based on the environmental or based on the physical effect and electrical fault. In the DC and AC side can be categorized. And the electrical fault, as you can see in the middle side, including DC like line to line or line ground or mismatching, open circuit faults, ground faults. And however, actually these faults also can be the consequences of some other faults, maybe actually can be appear on the PV panels. And that's important also you consider this and do the monitoring for the both side, electrical side and also the RGB or thermography analysis. However, actually just consider actually this interplay of the stressor on the component and its result of the failure mechanism and their effect on the module functionality and system functionality. It will be very complex and sophisticated. So that's important to actually use the novel method in order to detect better the failures. And most of these failures, of course, actually affect on the performance of the PV systems. And that's important. You detect these failures as early as possible in order to do the remedial action in order to keep the operational ongoing. So here are some examples like delaminations, bubbling, oxidations, and hot spots on the modules. So these kind of actually failures can be detected through the RGB camera or through the thermography analysis. And some of them also can be detected through the data analysis, through the normal monitoring systems connected in the AC side or DC side. And according to the statistics, the most failures occur in the PV modules, and some of the electrical faults also initiated from cabling failures and from the external sources. So that's important actually to keep actually monitoring. And in order to keep the monitoring for the larger scale plants, so you need really to apply the AI. And now is the question, what is the AI? And how we can use the application of AI. So in general, AI is a wide-ranging branch of the computer science, considering the building a smart machines capable of the performing tasks, which typically require human intelligence. And the AI can actually facilitate this. The AI technology is not, I mean, of course, new, as you can see here in this figure. I mean, the concept started maybe over 70 years ago, but the AI development was very fast in recent years and recent decades. And the reason was actually the data. So access to the data and the availability of the data. And that was the one of the aspect. And another aspect is increasing actually the advancement of the technologies and computational technologies and other technological devices, and both sensor hardware and software. So we have several different actually category of the AI. So in general, actually they can categorize as a learning method, as a like a machine learning, deep learning, and so on, and statistical methods and search methods and optimization theory, like a generated algorithm and maybe swarm optimization and grid search, for instance, and game theory and decision-making algorithms. And the concept of the autonomous monitoring analysis for photovoltaics and any, of course, applications is much relied on the application of the AI technology. So here, various faults of the grid-connected PV systems can be observed here in this figure, and most of them actually can be detected through AI application easily. So that could be actually about the AI monitoring for the fault detection on the PV array or strings, and power electronic converter faults can be detected, or fault in the filters or batteries fault or degradation can be detected. And also AI can be part of like other enabling and smart technology like a digital twin. So for your information, the digital twin create an approach for the monitoring and other services for the PV systems or any other systems in real time through the digitalization and virtual world modeling. And this approach uses for the intelligence analysis with the real-time data and gathering the information about the system operating status, and also including the decision making. So the AI has a much contribution also to apply for the digital twin. Typically, the AI, or let's say machine learning techniques, follow 5 steps. So starting from the data collection, cleaning and filtering, and train, of course, selecting the models and training the models, and improving the quality and quality of the data, and at the same time improving the model performance. So in machine learning based monitoring, which can be actually used for the autonomous monitoring, is learning algorithm can be used in order to learn the relation between the input output of the different variables of the PV systems. And this train model can be easily used for the autonomous detecting and classification of the fault. And of course, you need the data set, and this data set can be numerical or like a imagery data set, and it depends of the purpose. For the training purpose, we can actually use these models, different machine learning based models, and train the models and use it for the, for instance, fault classification or degradation assessment and evaluations. So in recent years, as you can see, actually, the trend of publications, there are a lot of machine learning methods applied for the detecting the failures, and also for the prediction or classification of the failures, and also use it for the reliability prediction. So in the next slides, I'm going to present to you actually some examples and related to our topic. And you will learn actually more about the how we can use the AI for the autonomous monitoring analysis, especially for photovoltaic system. So here we propose a machine learning based method for the line-to-line and line-ground detection and classification. So we use actually around 1,200 line-to-line and line-ground faults and normal events actually created. We had the system experimental PV systems development, and also we use actually different method in order to detect the data, collect the data and detect the failures. In another study, actually, we propose a fault diagnosis using the ensemble learning methods, and we use actually the supporting vector machine and navy base, and also k-nearest neighbor, and also we use it for only to detect the line-to-line faults. And the accuracy of this method were over 97%. In another study, actually, we developed a novel method in order to detect the hotspot and also bypass diode problem, and also disconnected problems on the PV module and strings. We use the conventional methods, I mean, like digital image processing, and also the convolutional neural network in order to detect the failures. And also we try to localize the failures, understand actually the localization of the failures that happen, and then do the actions, require action in order to, for instance, send the engineer to fix, or do further action in order to understand if the failure is real failure or not. Another example, which is related to the autonomous aerial monitoring analysis, and in order to facilitate the aerial inspection and make it fully autonomous, in order to use it for the larger scale plants, we applied actually the AI technology in order to make the drone and unmanned aerial vehicles as an autonomous UAV or drone, in order to make the procedure of the aerial inspection faster and, of course, accurate. And we have developed several methods in order to detect the failures as autonomous, and do the analysis and do the post-processing as a semi-real time. And for this purpose, we develop actually a software package. We call it RoboPV. So this software package is a novel software package for the autonomous aerial monitoring for the larger scale plants. And RoboPV actually can automatically perform aerial monitoring of any plant, completely autonomous, from optimal trajectory planning to image processing, pattern recognition, and real-time fault detection and analysis. So there are 6 units in RoboPV, including boundary detection, path planning, dynamic processing, fault detection, autonomous maneuvering, and decision making. So in boundary detection, which is very important step, for RoboPV, actually, we use it for the improve and optimize the path planning, during the autonomous aerial inspection, and we developed different algorithms using the digital image processing and deep learning techniques in order to improve the reliability of the boundary detection at the first stage of the autonomous monitoring. You see here some example of the plant for how actually RoboPV is able to detect the boundaries of each plant accurately in order to initiate the next step, which is the path planning. So we use actually several, we develop actually new data sets, and this data is available in the IEEE data port. So feel free to access it, and including the codes. So this data set, including around 3,500 aerial images from different plants in order to use it for the training our models. So the next unit is the path planning. So in autonomous aerial monitoring for plants, for PV plant, drone must fly over the set of waypoints, which cover whole area of the plants. And that's very important and essential to have a specific path planning algorithm in order to create the optimal paths for the PV plant aerial inspection. So that's why we developed like this unit for the RoboPV. So as you can see here, different plant has a different path planning models, and that's based on the waypoints we can detect it from each plant. Another unit is a dynamic processing unit. So we develop a dynamic path planning algorithm for autonomous maneuvering of the UAV during the aerial inspection. For this purpose, actually, we access to the flight computer of the UAV, interact with the onboard microprocessors on the UAV, and connected through API to the RoboPV. And through that, actually, we're able to send the command to the UAV, and in order, for instance, to the action if required. For instance, we define several modes like a home mode, flight mode, and maneuvering mode, and through that we try to use it for during the flight in order to make it more accurate and of course more safer. We had another unit as a fault detection. So RoboPV also including the fault detection unit in order to detect the failures, any failures which can be detected through the different sensors like RGB or thermal sensor or EL sensor. So we developed several algorithms in order to detect the failures. So here is an example for the detecting the bird drop failures. Another unit is actually the maneuvering unit, and that's also very important. During the mission, whenever actually any failures detected, the drone automatically can just detect it and then try to reduce the altitude in order to provide better overview for the detection, and also maybe better analysis, real analysis. And this maneuvering unit is responsible for this action. So, and after actually do the take a further investigation, the drone can back to the pass and continue the mission. And there is another unit as a decision making. So during the flight and of course after the flight and landing the drone, that's important actually to do some action. And this unit responsible for make a decision for the aerial flights and also for the detecting the failures and so on. I would like to show you a simulated version of the RoboPV. Of course, we tested in the real time, but here you can really sense what how actually RoboPV works. So here there is a plant, and this is a pass of the pass flight of the flight, and you can see only there is a failures here. So I would like to just run it. You watch it, what's happened. So in this plant, actually the string only affected by one faults, and you can see when the fault detected by the UAV, and the UAV has a maneuvering and try to reduce the flight altitude to 5 meters and above the ground, and it depends of course the condition of the plant, and investigate accurately and detect the failures. I would like to show you another example with 2 failures. So the flight started and the drone starting and follow the pass. And after reaching to the first fault and after recognize the faults, it's try to actually reduce the altitude and then just detect the failures and accurately and continue, and then the next, and then detect the next fault and then continue in order to fulfill the mission. And here is with the tree. Yeah, since I don't have much time, so I will try to skip. Yeah. So let's just summarize what we discussed. So as we discuss about actually the failures and the reason of the failures, and we discuss about the energy transition and increasing the number of the PV installation, and we are in the terawatt peak transition. And as I said, by middle of the this century, we need actually to reach to 20 to 75 terawatt installation in order to contribute to the energy transition. So recent developments actually aim to increase application of the AI, and of course we can use the AI application in order to detect the failures, any malfunctions or any other problems faster, precisely, and this is help. This is something actually can really help to increase the reliability and durability of the PV system and increase the lifetime of the PV system. Autonomous monitoring and analysis is the novel concept in order to integrate different techniques, devices, and systems in order to facilitate the PV monitoring for large scale plants. And that's very useful for the terawatt PV era. And also I introduced to you actually the RoboPV as a software package for autonomous aerial monitoring of the plant. Before finishing my presentation, I would like to introduce to you actually my our program in University of Freiburg. We have a continuation master degree program on solar energy engineering program. And that's in cooperation with the Fraunhofer ISE. So University of Freiburg is one of the 10 University of Germany, and also the Fraunhofer ISE, as you know, actually is the largest solar energy research institution. So we have this program based on our collaboration with the University of Freiburg and Fraunhofer ISE. So that's it. So thanks a lot for your attention, and yeah, feel free to ask your question. And also, if you want to have a collaboration with me, reach out to me through these emails. Thanks.
Oh, thank you very much, Professor Mohammadreza Aghaei, for this nice presentation. So it's a pleasure to have you today.
My pleasure too.
Yes, let's switch to the question if you have any question. So we have here a question from Mr. Ali Al-Habashi. So Mr. Ali Al-Habashi asked the question, when you detect a failure in an image of the panel, how you can localize exactly which panel was it?
So regarding the localization of the failures, I mean, one easiest way and maybe conventional way, actually, when you are detecting through the sensors, so you can just turn on your GPS. So then you can localize it. Of course, that's very conventional, and by using the like a new method, like using application of the AI. we are able to map the plant, and then of course based on the aerial inspection using, for instance, RoboPV or similar products, you are able to detect it on like a real time. So you know when and exactly which string, which panel, and even which part of panel actually affected by the failures. So there are several methods, but normally actually in the novel method, like autonomous monitoring method, everything will be some like a real time or semi-real time. So you know about where you can find the failures and do the remedial action for it.
So thank you very much, Mr. Mohammed, for this response. So for the other participants, if you have any question, so we will take a 5 minute Q&I to respond for your question. Yes, we have another question from Mr. Abdelali Abdessadek. So to apply a digital twin technology in CSP, what are the most commonly used software programs?
Actually, digital twin concept, as I said, is not only rely on one software. So you will use, actually, you can use several like hardware and software technologies in order to implement the digital twin technology for any applications, including the CSP. So in my point of view, actually, you should consider actually the real cases and simulated cases together, and the measure cases. So that's important. You actually have access to the data and can, I mean, through API or so on, access to the data, measure data, and at the same time you have actually, I mean, the virtual environment in order to model the systems, and then you can apply actually the AI in order to use the application of the AI in order to detect any faults or any anomalies. And at the same time, you can develop further your models and try also to use the new models for actually detecting the failures. So it will be like a several stage in order to implement the digital twin-based monitoring or control. So that's not easy, of course, but takes much time, and also you need actually much fun for it. But there are much progress on this, and in the photovoltaics and CSP, I didn't see much actually like a real case using the digital twin approach for in order to complete the monitoring of the autonomous monitoring of the plant.
So we have also another question from Mr. Musab Idrisi. The question is, what are the hardest failure mode to predict so far?
Can you elaborate more? I didn't get
Yeah,
what.
yeah. So Mr. Musab Idrisi asked about the most hardest failure you
Oh,
detected.
okay.
Yeah.
Yeah, I just show you actually in my presentation one graph about what is the most common failures, but I can tell you just yeah, by some example. But for instance, in the PV system in power plant, most of the failures happen in the PV modules, and also in the maybe part of the BOS, for instance, in the cabling. And in the PV module itself, most of the common failures is belong to the like a breakage of the glasses, and uh, and also some part of the like a junction box of the modules and the electrical part of the modules. But of course, it depends of the location of the installed PV systems and the conditions which is actually under operation the PV systems.
Yes, Mr. Mohammed. So we have also two questions. The first one from Mr. Tijani Khalil. So he thank you for your presentation, and he
My
asked you,
pleasure. Thanks.
how much is the scale of the PV project your software can go for?
There is no limitation. The only limitation is actually uh, the number of the landing and takeoff. And of course, there are some solutions in order to facilitate this. And because I mean, this software package can be integrated to any drone. So if the drone is electric based, then the timing actually the endurance will be low, but it will be if the drone is like a fuel base, it will be much fast, much longer takes. So in general, I can say, okay, I mean, you need when you use this software for 1 megawatt, you need only maybe less than 30 minutes in order to cover all plants. And of course, doesn't mean actually if for instance, you increase it to 10 megawatts, then you need to times it to the 10. No, because then you can actually, I mean, use maybe fly in higher altitude, so it takes maybe even low. So maybe you need maybe 2 hours to cover 10 megawatts, for instance. So it depends.
Thank you very much. So the last question is in the hot region, the sensitivity of the drone camera decrease. So how you can skip this issue?
Could you repeat it?
So yes, the question is about the sensitivity of drone camera in hot region. So how you can skip this sensitivity effect
Yeah.
in hot region? Yeah.
I mean, there is some report about that, an experimental report. I did some experimental report and work on that. But in my point of view, actually, that's very important. Of course, if you want to use it, for instance, if you want to send the engineer and do the normal thermography, there is a instruction how you can do that in order to avoid. And if you want to use like a drone for the aerial inspection, that's also important. You consider like the angle of the drone. So of course you should consider the field of view of the camera, and at the same time the angle of the camera toward the PV panel. So that's important. Before that, you do some like a pre-analysis of the region, and also when you are going to do this inspection, what time, and that's important. Maybe in those area, maybe the best would be you go for the inspection early morning, not exactly at noon, because then you have some unreliable information. Maybe the reflection can affect, and also maybe that's also impact on the sensitivity of this thermal camera.
So thank you very much, Mr. Mohammadreza, for this nice presentation and also for
Thanks a
this
lot.
nice response to all of these questions. So it's a pleasure to have you today.
It was really pleasure, and I'm really appreciate for again from the organizer and from the participants. And yeah, so I hope actually you enjoy the rest of the day and enjoy from the other presentation from my colleagues. Thanks a lot.
Yeah, you are welcome. Thank you very much. So after this nice presentation of Mr. Mohammed, let's switch to the next presentation of Mr. Fabian. So, Fabian,
Hello,
are you with
everyone.
us?
Thank you. Can you hear me?
Yeah,
Yes.
of course.
Oh,
So
okay.
let's give a brief presentation of Mr. Fabian. So Mr.
Yes,
Fabian,
thank you.
after his graduation as a physicist at the University of Munich, Mr. Fabian did his PhD in solar energy engineering at the German Aerospace Center DLR. He led multiple international R&D projects in the field of energy, meteorology, and Stalin, image analysis, sensor development, and performance analysis for both CSP and PV technology. So, Mr. Fabian, it's a pleasure to have you today.
Thank you. Thank you very
Thank you
much
very
for the
much.
kind introduction.
So yes, please, the floor is yours.
Thanks. I hope you can see the screen. Is that correct?
Yeah, it's okay. Thank you very
Yes.
much.
Okay,
Yeah.
good. So I'll talk about our solutions like Volateq's software suite for aerial solar field inspections. So it's all about drones again. So I saw some things that will come up here again regarding drone inspections for solar fields. So who are we? We're Volateq. We're a spin-off of the German Aerospace Center. We were founded in 2020, and we provide software as a service services, for the inspection of utility-scale solar power plants. We have both markets, like we started in concentrating solar power. We cover now more than a quarter of the global CSP installed capacity. And we entered the PV market where we can and have already clients, and we're working there since, like, let's say 3/4 of a year or something. Our focus is on innovation. We have a very strong focus on automation, repetition rates, which is more important in CSP than in PV, but we transfer all those learnings to the PV. So I'll go into the details to the agenda now. So first of all, I'll give you a little bit of an overview of the two technologies, CSP and PV, just to make sure, or just to let you know that these are two very different kind of things. Especially what to look for is different in those two technologies. Then we'll analyze a little bit the markets, like for inspection. Then I'll go into details on failure detection in both technologies, and also let you know where the challenges are and where we apply AI. Then how do you work with us? Like, how do customers work with our software? So we could walk through data acquisition, the data processing, and also the displaying of the results. And then I'll give a little outlook, and we have the same question and answer session in the end. So CSP, I don't know, most of you might have heard of it, especially in Morocco. It's a big thing, like in Ouarzazate, there's a few plants, and there's even more plants throughout the country. I've visited a few of those. So it's 8 gigawatts in total global installed capacity. And the main advantage over over PV is that we have the cheap storage option. So basically you have mirrors that concentrate the sunlight to produce heat, more important than just a big heat storage. PV, in contrast, is much more successful, especially during the last years. 1,500 gigawatts, I think, in 23. It's rapidly growing, so don't take this number. It might have been much higher already. So you produce electricity instantaneously, use diffuse and the direct irradiance components, whereas in CSP you only use the direct irradiance. And about 50% of PV installations are utility scale projects where you would use PV drone technology or more sophisticated monitoring to control those plants. Prospects are also good, like it's 20% in annual growth of the growth rate, so it's exponentially growing, and it's basically very, very cheap and cheap technology and endless use cases. At Volateq, we work with both, as I said before, like PV and CSP plants. Both technologies can be inspected and need to be inspected with drones. So this is just a little bit of an idea what you can gain by running a power plant in the most successful manner, or most controlled manner. So if you have a 100 megawatt CSP plant, so this is a CSP plant example. It's not that every plant works like this or the numbers are the same, but you can assume in a place like Morocco that this plant produces like 250,000 megawatt hours a year, and this converts to 25 million euros, assuming a price of 100 euros per megawatt hour, which is also dropping over the years. But we see that roughly you can lose, or we see that some plants lose up to 4% in efficiency. So that converts then to €1 million a year. And the very old-fashioned, so to say, inspection, operation and maintenance procedures also are expensive, because you have people in the field that walk around or drive around the field and look at everything, every component. That's costly. Also, safety can be an issue. So that sums up to 1.2 million euros a year, which can be saved if you replace that by more sophisticated, optimized drone inspections. A typical average assumption that you find in literature is basically half of that. And in PV, it's less because PV it's just more simple, to put it like simple. So one assumption that I found is 220,000 a year of loss in revenues due to insufficient operational maintenance. So if you employ aerial inspection in such a field with us specifically, you can gain clarity. So you know what's happening in your field, you know more details on what's going on there. You save resources, so people in the field do not have to walk around the field looking at faults themselves. They win time, they win autonomy. So if you have, this is a special application case of a software as a service, because we enable simple field technicians to fly the drones themselves. So they don't have to coordinate with an external drone pilot. So they can do the analysis whenever they want. And in the end, of course, you improve performance, which in turn increases the profitability of the plant. And that's what actually counts for the operator in the end. So now coming to the technical details of failure detection itself. So first, CSP. CSP plants are vast. So this is an example from Spain where you have like 150 megawatts, what you see in this image. It looks all the same. So if you're driving around that field, you get lost, basically. So what can go wrong in such a field? You have the tube, which has to be accurately placed in the focal line of, or focal point of that parabolic trough. If a mirror is misaligned, that ray is not reflected onto the tube itself, but it misses the tube, and the irradiance, of course, is lost. So you need to know exactly where those mirrors are facing and where they're facing wrongly. And we solved this issue, and we can measure the alignment of the mirrors with high precision. So this is in milliradians, and you can see on the color scale, green regions are hitting the tube perfectly, and as soon as it goes into the reddish or bluish direction, then the rays will miss the tube. Also, the tube placement itself, like if it has an offset in any direction, that's something bad. The mirrors can be placed well, but if the tube is not aligned perfectly, then the rays do not hit the tube and it cannot be converted to electricity. Basically, we detect from, this is a drone image actually, so we blurred out the background, so you can only see the parabolic trough, like the mirror surfaces, and you can see this black area, which is actually the tube. It becomes bigger because from far away, the parabolic trough acts like a lens, and you can see those dips here. So this curve here, you can see my mouse correctly, do you? Yes? Well, on the right-hand side, on the very right trough, you can see that this line is like snaky and shaky. And that means that the mirrors are not aligned perfectly, or the tube just wobbles around a little bit. So this is like a loop effect here, which we use to detect failures. Same thing here. So the concentrator alignment, so if one concentrator here, you have a shift, obviously, on the right-hand side, you can see that the tube reflections are on the left in the upper part of the image and more on the right in the lower part of the image. So the entire collector is misaligned, so it's not tracking the sun perfectly. Then also glass breakage is an issue. You can see it on the left-hand side where there's mirrors missing, and you can see the ground below those mirrors. That's another issue which is happening quite a lot in CSP plants. There's many more of those technical parameters that we detect here. These are some of our product packages that we offer for the CSP technology. So the heat collecting elements, temperature, and also advanced analysis, collector package, concentrated geometry, the mirrors and the tube location, torsion, if you have some torsion along a trough, the alignment, glass breakage, and you can then book in our case, you can book packages of 1 measurement a year, 2 measurements a year, or 12 measurements a year. Actually, some customers are even going higher because they want to track errors and faults as soon as they come up with even weekly frequencies. So that's in CSP. There you can see that the measurement frequency is much higher than in PV. So PV is my next topic here. I'll show you a little bit the working principle of our PV workflow. So as we take images of the field, you can see original images on the left of this slide. We created a digital twin before that. So that's done either during the first flight, like by image analysis, we create a digital twin. But at this point, the software already knows where it has to expect modules. So it knows more or less accurately how the field is built. Knowing that, we can, from the GPS signal together with the camera orientation and some more magic, like we do not rely only on GPS because it's only accurate to a few meters, and a module is just in that range. So there's a big source of error if you only use GPS to miss the module or to say that the fault is in another different module than the one that you say actually. So we need to double that up, not only GPS, but also triangulation of from module lines to know exactly which module we're talking about. So in and the same module appears in multiple images of a measurement flight. We have like 5 or 7 images of each of those modules. We cut them out. We create a so-called ortho image. And then of those ortho images that correspond to one and the same module, we then run the thermographic failure analysis one by one on each of these modules. And then we categorize the errors or the non-errors on those modules. And then we can feed that back into the digital twin. So on the bottom here on the right, you can see our web app where we display, in this case, I think it's soiling, medium soiling, so that's why there's so many errors here. But you can display, let's say, bypass diodes, which is the upper case in the actual ortho images, which you can see here. So that's basically our basic workflow that we apply here for the infrared images, and that in parallel works also for the RGB images. But anyways, some fault types, we've seen them before. So there's hotspots, for example, then you have shading here, which causes a slight temperature increase on the entire string. You have disconnected modules, and all that can be detected. Sometimes you have question marks, like this one here. It's a colder string or a colder table within the entire plant. So that's weird because you only see heating up modules, or you can see a hotspot here, but which seems like a normal hotspot. But as I said, we look at the RGB images in the same flight, of the same flight. And here we can see in this case that there was a bird dropping on that cell, which caused this hotspot. So this tells us that the operator does not have to exchange that module, but he just needs to clean it. And it would be a loss of a few €100, including the technician to exchange that module, if he exchanged the module, no? So cleaning is a much easier task, a much cheaper task. And in this case, the colder module, of course, there was a cleaning machine at the same time going through the field. That's why the water cleaned that module. Then another product that we have, I think we're the only ones offering this product on the PV market. That's the soiling ratio. That's something that was developed at DLR by myself, actually. And we have to license that from DLR as for marketing within Volateq. The detection is analytic, still 100%, but of course we're not omitting including AI methods in this method here. So you need to do a one-time local dust calibration in order to get some kind of some images of that kind, like here in this plant, in this example, some modules have been cleaned, like in the lower row and in the upper row, to produce also clean or contrast to clean modules. And you can see a typical pattern which happens in many PV plants, which where the dust is just washed down to the lower cell string or cell level here. So we can actually measure entire solar fields, the soiling distribution over entire solar fields. The accuracy is, well, absolute. It's hard to quantify, but the main reason why it's hard to quantify is because of the reference measurement. So the reference measurement for soiling is, yeah, not so reliable. And so we say that we specify by 2%. We're really good when comparing soiling levels within the same field. We don't know all too much about how the absolute value corresponds to the actual losses for soiling, but they're quite good still, or at least we're confident. And we measure that on the cell level. So that's also one advantage over other devices that are on the market. So in PV, we offer 3 packages of products, basically. So first, according to the standard, that's basically flying at below 20 meters, just below 20 meters to get the right resolution. The survey is enough as of accuracy for most of our clients. So it's flying at 40 meters altitude, and PV soiling, usually from the flying, it's the same flight routes. You can use the same or just one flyover of the field, and you get the PV soiling package also. And you can fly yourself, with a pilot, with some solar field technician, buying your own drone. Then you're autonomous, or we're about to launch our drone in a box package. So we're working on this. We have a test running. I'll come back to that later. So AI, so that's the topic here. Our foundation of the analysis is all analytic. So we started off analytic. We have a very profound and deep knowledge of image analysis, which is basically all analytic. But of course, AI, we don't want to discard it, and we're including it at specific and well-defined points. Mostly where we see that we have to interact as the programmers before handing out the data. We had to review data. We had to correct some details in the analysis, in the results. And that's one of the main points where AI has helped us a lot. And also we want to improve performance at specific points. We can increase the accuracy at specific points, but we still want to be in control of what the AI is doing. So that's why we decided to choose the best of both worlds, to not have a black box with just a training data set, which somebody labeled, and then you cannot improve the entire thing at specific points. And we still don't want to, we still want to profit from this potential of AI at specific points in our workflow. So that's basically our philosophy of implementing, of integrating AI into our software here. And we see great potential. So it's not about saying that AI is not good enough or something. We just don't want those black box. This is for us one of the major arguments to still have the basic analytic workflow running in our case. So how does it actually work? If you're a client, how do you actually measure with us? How do you get first measurement results? So step 0, it's up here, it's on the left. We need to know where your panels are. We need to digitize your plant. So we need to create a digital twin. This can be done either during the first flight in the same flow, or we just have a perimeter in Google Maps, and then this can be digitized. So there's various models of how to do this. But once this is digitized, it's just one time. Then you can repeat the other steps as often as you want, which is, of course, you need to acquire the data. This usually works with the client itself, having bought one drone and having somebody in his team who can fly the drone. Then the data analysis happens that's our job, basically. we provide, of course, we provide the pilot with the flight routes. They are designed based on the digital twin. So we do the analysis, and then you can view the data in our web app, where I come back later also. So you get health reports, you get actionable steps for optimization, and of course the feedback here from our clients is invaluable. What they're looking for and what they actually use and what they make of our data. So how do we digitize this? So from Google Maps, we have software that recognizes panels and strings of panels and tables, and then converts it to a layout plan of this PV plant. So the software knows where to expect panels. How does the data acquisition work? Well, we have several ways of connecting or of transferring a flight route to a controller or to a drone in the end. So for DJI, we can use the DJI, DJI is a manufacturer of drones, so the most known manufacturer. We can like upload the DJI, the flight route directly to your DJI account. So you can use that directly, or you can use Litchi. And we also built our own Wolfertstetter app, which can be uploaded to the controller, which is nice because it's easier. Like our intention is to make it as easy as possible for the user. And here, all the camera settings and stuff is already preset in our application. And in the other two applications, you need to do it your own, which is not a lot of steps, but still there's some source of error here. For flight parameters, flight height is between 15 and 40 meters in photovoltaics, a lot higher. It can be a lot higher in CSP. Flight speed is 5 meters and 10 meters. And like image overlap is also one question that we get a lot, but we're working with videos. So we take videos and then we can just chop this video into separate images and then define the overlap ourselves or control it ourselves after the flight. And we use, of course, the DJI tools, which are really nice in terms of anti-collision and flight restriction zones. Once you've flown your drone, then you need to upload the data to our portal. So that's how that looks. It's pretty easy. Just need to select your plant, the acquisition date, and then upload that. And you can also, in this portal, you can also, if you want to do another analysis another day, you can also require, or on demand, you can demand your new flight routes for that day. This is the results presentation. Then you have a map, basically. Errors show up in color. So this is a CSP plant, if I'm not wrong. Yeah. If you click on something, then you get all the details shown in a pop-up window. You get some statistics and a legend on the left. You can switch to table view, statistics view. You can get a history of measurements. And of course, we have all the transfer protocols installed to like integrate our measurements into your plant measurement management tools. But you can use our software also as a plant management tool. So add own observations, take an image if you're in the field. And of course, if you take your device into the field, like a mobile tablet or even a mobile phone, you walk around just like in Google Maps. You can see your blue dot where you're walking, and you can turn around and you know that you're looking at the fault that we detected. And this makes it very easy to work with. And there's also an offline mode, which is an issue in many plants where you don't have stable internet. You can just download the results and then walk around anyways and have everything available without stable internet. So to sum it all up, we provide very high level of automation because you can just repeat that. The flight routes are automatically created, and yeah, it's very automated. And you can be independent. You do not need to call in a pilot. We just have our software and we do all the rest. We have quite a nice way of presenting the results, and it can be applied by anyone. It's actually dead simple up to now. And it's an all-in-one solution. You can, of course, apply it globally because it's just software. So where we're going, drone docks is a big issue for us, or a big topic for us. We're just testing a few different models. CSP has, like in CSP, there's a bigger potential of application of drone docks, docking stations, totally autonomous drones. And then in PV, you have to look for the application cases, but large plants or high loss rates are, of course, some of the target areas. And then other development lines, like we're collaborating with a company where we actually want to fully integrate our inspection results to a monitoring software in PV. And we're working on applications for Aghaei photovoltaics, where we combine crop health monitoring with thermography. We're used to complex geometries from CSP. So as soon as you have PV installed in complicated buildings or something, that's something where we are at home. And desert climates is also something where we learned a lot in CSP. So that's these things we want to bring into the PV sector as well. And of course, we're open to any kind of partnerships, cooperations, and research. Yeah, that's our team. We're growing, so there's even actually two persons that are not in the pictures here. Yeah, so that was it from my side. I'm happy to answer any questions.
So thank you very much.
Oh, yeah, okay.
Thank you very much, Mr. Fabian, for this nice presentation. It's also a pleasure to have you today. Yeah, thank you very much.
Thank you.
So let's switch for some questions. Starting with the first one, the question for Mr. Mohsin Rami. Yeah. So is drone inspection sufficient for overall inspection of large-scale solar PV plants, especially when we have a central inverter and cannot inspect each string separately?
You can inspect strings separately, of course, but once you have a drone in the air, you want to typically measure everything. So that's something that we're investigating. If you have a monitoring software which tells you that something's not working right in one corner of the field, let's say one string, of course you can send your drone there, but yeah, so it's probably not the most practical way for inspection. The first part of the question was, can you repeat that? I can't remember the first
question. The question about the sufficiency of the drone inspection. So can we consider that drone inspection is sufficient to inspect the overall large-scale PV plant?
Yeah, it is. Like it's the way. It's very established already in PV technology, so that's what everybody does. Of course, if it's about insurance issues or something, you need more advanced technologies than just thermography. Let's say you would need electroluminescence, but that's very advanced and much more costly. So to get an overview of the state of your field, then thermography, the drone inspection is sufficient, yeah. Well, you always need both. You also need the monitoring because you cannot fly every day with thermography. The monitoring covers that part. So with the monitoring software, where you get all the data from how much output do you have from your solar plant, you get usually alarms if something's running wrong instantly. And with drone software, you just get it once you fly. So that's usually once a year or something.
Yeah, thank you, Fabian. So we have also another question. So for other participants, he thank you for your nice presentation and ask you about how can, as a developer, benefit from this application by integrating your APIs?
Depends on which kind of developer you are, but if you're interested in getting your in getting our results to your software or to your developments. Of course, we can design like a API interface, and then you can request the values for any part of the field, and we can give them to you. So there's a geolocalized information of every module, which we can pass on directly.
Yeah. Thank you very much. Yes, let's take a last question, Mr. Fabian. There is a lot of question about your presentation. It's very interesting. So the last one, to switch to for the other presentation. Thank you. So the question is, what is the minimum capacity when the inspection by drone be useful and economically competitive? It's very interesting question.
Very good question indeed. Yes. So if you're an owner of, let's say, 500 kilowatts, so small plant, rooftop or something, and you ask us for just one flight, we might think twice about getting you online, because all the overhead of, communication, everything might be too expensive. But if you're, let's say, a drone pilot or drone service provider, like if you have drones and you do images on a daily basis and you serve a multitude of small plants, then for us, that's a different story. So it's in principle, it's applicable to small plants, but the cost benefit economics, you have to look at that twice. And so we do both, like we do large plants where we actually provide our services to the operators. And then we do like service providers that take their drones to a multitude of small plants, and then the sum sums up to an economical viable case.
Yes, thank you very much, Mr. Fabian, for this nice presentation.
If you allow me, there are just one question for Fabian.
Yes, sir.
So thank you so much, dear Fabian, for this interesting presentation. So based on your experience, could you tell us about a real project that you are following, and what is the impact in terms of CapEx and OpEx? As well, have solar farmers adopted this type of smart operation and maintenance solution or not yet? And thank you again, dear Fabian, for your presentation.
The CapEx is pretty easy. Like the CapEx is, let's say, 5,000 euros for one drone. So that's the CapEx, nothing more. Then the OpEx, that depends also. Like we cannot offer, I cannot tell you one price per megawatt or something, because it depends on the circumstances. But in many cases, especially in CSP, in PV, the technology of drone inspections is really state of the art. So there it's used everywhere, and it's very common to use that technology. So we're just one player among many with our own advantages. But in CSP specifically, we can see that people are not used to this kind of inspection. And there we see that people appreciate, like once they tested our technology, they never want to go back. So the example we gave before, that they can save millions in a 100 megawatt plant over the lifetime of a plant, it's not hard math to see that it works out for the operator. Only the value for saving, let's say, manpower to manually inspect collectors, that's already enough for many of our customers. That they say they don't have to have two people running around the field all day long to do the inspection work. If they save those, that works out economically for them already, to replace those two workers by drones. Yeah.
Yes,
I hope that answers the question.
Yeah.
Thank you.
I hope so. Thank you very much, dear Fabian, for the nice presentation. So I hope we can collaborate with us and with all the participants for the future. Thank you very much.
Yes.
So thank you very much. So let's switch for the next presentation and the next speaker, Mr. Marc. Mr. Korevaar. Yeah. You are welcome. pleasure to have you today.
Thank you very much for the introduction, and thank you for organizing this nice workshop and giving some moments to say a few words. I'll put on the
Yes, Marc. Let's firstly start with first introduction about yourself. Yeah. Thank you very much. Thank you very much. So let's start with first presentation of Mr. Marc. So Mr. Marc Korevaar received his PhD degree from the University of Technology in 2015. So for his research on applied physics, since 2015, he works at Zonen in research and development. There he is involved in the development of new solar energy detector, their calibration and radiometry. Kipp and Zonen is a leading manufacturer of measurement instruments for meteorology and solar energy. So Mr. Marc will present artificial intelligence measurements in irradiance for solar photovoltaic and solar CSP. So Mr. Marc, please, the floor is yours.
Thank you very much for this introduction, and thank you very much for organizing such a nice workshop on this topic. And I will say some words on radiance measurements and what we have sort of researched. You know, what can AI do in these cases? And I will also touch on PV plant monitoring and AI related to that. I will first say a few introductory words about the company that I'm working at. It's called Hydromet, but Kipp and Zonen is part of it. And Kipp and Zonen makes the solar irradiance sensor and atmospheric science sensors for meteorology and solar energy. And we have also got sister companies such as Luft, which make the weather stations and other meteorologically related sensors. And we also have Meteostar, which is making software for weather forecasting. And yeah, I work for Kipp and Zonen in the Netherlands. So when I was asked to say a few words, I was thinking, okay, now what is from the perspective of the company where I work important? Now what can we contribute? And then we thought that the end goal is that we can have stable and optimal energy production in a PV plant or in a CSP plant. And for this, fault detection and good maintenance is important. And from a company as Hydromet, we think that we can help and support this by making more accurate measurements and available to the analysis that there is. So yeah, can we make irradiance measurements which operate better with artificial intelligence? And if we measure things, which measurement parameters are important for AI in PV plant analysis that will enable fault detection and good maintenance? So first, I will talk a little bit about the radiance sensors and some of the experiments we did and how can AI help improve that. And we believe that when we are able to measure irradiance more accurately, we can also improve the capability to detect that something is happening in the plant. And the second part will be a PV plant case study where we will look at, okay, which kind of measurements are beneficial for AI in the plant. And then I will wrap up with a summary. So I will start with one of the products that are made by Kipp and Zonen. It's called a pyranometer. And this comes from a Greek word, or Greek words, pyra, ano, metreo, which stands for fire having measure. And it can be used to measure the global horizontal irradiance when mounted horizontally. You have variants which use a silicon diode for measuring the irradiance, or the thermopile, the higher classes of pyranometers. And often in a photovoltaic plant, you see them mounted plane of array, or sometimes referred to as global tilted irradiance, to measure the irradiance that falls on the surface of the PV module. Now, we have done some comparisons in Delft of different instruments. We have a class A pyranometer, that's the highest class on the left. We have also considered an SP Light, class C pyranometer, and an RT1, class C pyranometer, which includes a back of module temperature sensor, and in addition also a working class reference cell. This is a photo of the setup next to PV modules. We have the different sensors mounted in the same orientation as the PV module. And when we look at some results of this work, which has been mainly done by Samit Karki, we see that there is a good linear, as expected, linear relation between the class A pyranometer and the class C SP1 pyranometer. And we have done a bit more in-depth analysis of these measurements in a so-called box plot. And here on the y-axis, you see the different sensors. And on the x-axis, you see the difference with the class A, the highest class pyranometer. And then you can see in this blue, the interquartile range, which is giving 25% and a 75% distribution. And these whiskers, they give the 5% and the 95% distribution. So you see sort of the distribution, how much does this particular sensor deviate from the class A pyranometer. And we see that there are differences. One of the photodiodes is spot on when it comes to the calibration, but all of them have some variation. When we dig a little bit deeper where this comes from, this variation, we find a number of things, and that is a relationship with the air mass, or the angle at which the sun is at a particular time of the day. We find a relationship with the temperature. We find a relationship with the spectral redshift of the solar spectrum at that particular time. And we can see that for some sensors, when you look at this graph, the air mass is here, the difference with the class A pyranometer is there. There is a considerable relation with the air mass. And there's one sensor, the blue one, which has a fairly constant response, although still some variation exists. And we thought this is quite a complex interplay. We have temperature, we have angle of incidence, we have the spectral change, we have the air mass change. And we thought this could potentially be something where artificial intelligence can be beneficial. When the problem gets quite complex, then it can be beneficial. So work has been done on this, and we have tested artificial intelligence, and the way we did it is that the data was processed. Usually a little bit of outlier filtering and filling of data gaps is done. Then this data was given as an input, and we used an artificial neural network for this, and we obtained a predicted output. When we dig a little bit deeper in how this worked, is that we had the input, we have a backpropagation neural network with a number of hidden neurons and the output, and then a cost function that looked at the output difference with the input was fed back to the hidden neurons. And then in an iterative way, this allowed us to train this network. Now, a bit more in detail shows you which kind of inputs we used in this example. And as an input here, we had the temperature, the air mass, which is sort of it's dependent on the angle, the zenith angle of the solar irradiance, and the input from the Class C sensors. And then at the output, we had the Class A output to compare with. And then after training of the network, we obtained the predicted output. And here you see what these sort of box plots of these outputs look like. And in the black, you see the let's say unimproved result, and in the red you see the same sensor but with the AI improvement. And in all cases we see that the AI improves the measurement accuracy, and mostly sort of it shifts the difference, the median, closer to 0. And there's also a reduction in the variance, or let's say the precision is improved, but that, yeah, some variation still remains. That cannot be taken away completely. But that's a general picture that we see, that there is an improvement. Now it is still a question like, okay, how reproducible is this result if you would vary the location, or if you would vary the installation setup of a particular sensor. If you make a sort of a hand waving guess at the uncertainty that sort of is left compared to a Class A, we could come to roughly 2%. And if we go into the uncertainty of the sort of the AI enhanced Class C measurement result, then yeah, with a Class A parameter, we start at roughly 2%. This can be calculated with a calculator that's available at the Google App Store from Kipp and Zonen, by which you can calculate the measurement uncertainty in the field. And we've seen from the previous slide that the rough estimate of the AI variation would be about 2% uncertainty. So if this could be included in a straightforward way, we would end up at roughly 2.8% root mean square error. So it's not as good as a Class A sensor, but it could be better than it is. Now, as another follow-up question, where we have not worked on yet, is could we also make a Class A parameter perform better? And then we were starting to think like, then we actually need to train it with the best irradiance measurement method available with the lowest uncertainty, and that's with a tracker, with a parheliometer that measures the direct irradiance, and with a parameter or 2 parameters measuring diffuse. These are some pictures from Acciona Energy, and yeah, when we look at the uncertainty that we could achieve with a tracker solution, here we see a plot of the KS2 uncertainty over the day. We see that we could go below 1% or down to 1% with a tracker, and with a current Class A parameter in the same site, we would be at roughly 2% at best. So yeah, the question is, can a Class A parameter be trained with a tracker? And yeah, I'm afraid I'm having more questions than answers at the moment. So as to how to do this, and how to translate the training to different climate zones or tilt angles, and how low could the uncertainty go of Class A parameters? So this is a question, and collaboration is welcome on this topic. Now that I said a few words about the irradiance sensor, I want to sort of zoom out a little bit and look a little bit more at the bigger picture, and then looking at the PV plant, and see if sort of this method for a non-ideal Class C sensor, if it can be translated to a PV plant, where also you have a complex interaction of many different parameters, and even more complex than with a Class C silicon parameter. And So we're going to look at the PV plant, and this is work that Sajjad Badalkhani has done. And when we look at the PV plant, we have a lot of things that determine the output. For now, we're going to focus on the weather and the environmental factors, such as the solar irradiance, the ambient temperature, the wind speed, the direction, the precipitation, and the soiling. Now, this is a concept of how to, independent of the irradiance, determine the performance of a PV plant, the performance ratio. And I'll quickly say a few words about it. It is sort of the ratio of the measured energy to the expected energy. And in formula form, it's here. And the solar irradiance determines to a large part the power output, but ideally the performance ratio would be independent of the irradiance level. But in a bit, we'll see that that usually is not the case. Another factor that greatly influences the PV plant power is the temperature, because when the temperature is higher, the PV cell efficiency drops, and then the PV plant generates less energy. We have the wind speed, which is the way that the PV plant modules can be cooled, thereby enhancing the efficiency. We have precipitation, which sometimes is beneficial in case there is soiling on the modules, but on other moments it can also block some of the irradiance, or in case of snow, it can block a lot of the irradiance. So there are different effects depending, amongst others, on the temperature. And of course, we have soiling directly, which absorbs the light, and it negatively impacts the efficiency of the module. Now, to see a little bit more, there's a case study done in Japan where we, from a plant, have obtained the calculated performance ratio over time, together with the global irradiance and the plane of array irradiance and the power output of the plant, and the ambient and the back panel temperature, as well as the precipitation and the soiling, and the wind direction and the wind speed. And when we make a correlation matrix of all these parameters, we get a picture as follows. You see the parameters on the y and the x-axis, and a red color indicates a high correlation, and a blue color indicates a low correlation. And I'm not going to go into all the details, but focus a little bit on the power output of the plant, and then we see that it heavily correlates with the irradiance as expected, but also with the rear of module temperature, the ambient temperature, and the wind speed. And yeah, with the help of these kind of correlation matrices, which are of course site specific, some sites will have other correlations, we can see a little bit which are the important things to measure in order to learn how the plant will be doing. Now we can apply these measurements also for a artificial intelligence algorithm, and that has been done with us, and you can see the results on this page. We have applied 4 different models, each with different inputs. So model number 1 has global irradiance as an input, and in this slide you see the classification as to how important is that particular input in that model. With one input, of course, the predictor has 100% importance. Model 2 has added also the temperature of the module, and the ambient temperature, and the wind speed. Model 3 has added soiling, precipitation. The 4th model has the most measurement parameters. When we look at the results of these models, we see different performances. So the performance is visible in the red line compared to the blue line. The red line is the actual power out, and the blue line is the predicted power out. And you see with the root mean square error on the top of the graph, a numerical evaluation of how good the prediction is. And the first model does somewhat of a job, but not that good. And when adding more sensors and more inputs, you see that the root mean square error value gets better and better. So yeah, with model 4 having most of the predictors, then we get the best match between the predicted and the actual power output. As a small last sidestep, I will go a little bit into satellite data. So satellite data is also available. We've looked at satellite data from NREL and of a small tract plan. And mainly we focused at, okay, if we compare this satellite data with ground measurements, how well do they overlap? And then generally, we can see that for all of the measurement parameters, that on a yearly basis, it can be somewhat accurate, a little bit depending on what kind of thing you're measuring. Like for wind or for global, it's fairly accurate. For plane of array, somehow it is not that accurate, but yeah, for most of them, it's relatively accurate. But if we go to very short time frames, maybe down to 5 minutes, we can see that the satellite data becomes less accurate. And to come sort of to a bit of a conclusion is when we take ground measurement and satellite data and we feed that as input into a modeling or an AI approach, we can better predict the PV plant output. And when we can predict it and we see what the actual output is, we can start to see if something's going wrong in a plant, if somehow we have a large underperformance based on the prediction. And that, we believe, will help do a good job of maintenance and to show some of the instruments that Alt-Hyderman makes for accurate measurements of these parameters. We have here the parameters. This is an overview of the different parameters for the different applications and the different accuracy classes. We have the dust IQ for accurate soiling measurement, and there is the series of weather stations which allow you to measure a large amount of meteorological parameters, including also back of module temperature with an external temperature sensor. So in summary, we've seen that Class C sensors are not as accurate and precise as Class A sensors. However, when using artificial intelligence, the performance of these sensors can be made more accurate and also somewhat more precise, but not as precise as a Class A sensor. And we would be interested to find out if we can use AI also to improve the Class A parameter performance. And a PV plant case study showed that with weather parameter input, you can get predictions of the plant power output. And with that, I'd like to thank you for your time and attention. We would welcome a collaboration or a partnership or research, and it can be reached at this email address. And I would like to acknowledge Samit Karki and Sayat for their input, and thank the organizers for giving the opportunity and this nice workshop.
Thank you very much, Mr. Marc, for this nice presentation. Thank you very much. So let's switch actually right now to some question. The first question is for Mr. Greg Smith. So it's our distinct honor and privilege to have with us Mr. Professor Greg Smith. So Mr. Greg. Thank you, Marc, for your nice presentation. And he asked you, I would like to ask you comment on such measurements for bifacial module. So how it is best to do this, and what are the caution and caveat where can learn more about this issue.
Thank you. Yeah, nice to hear a question from you, Greg. Yes, this is a important topic, and my feel is it's still something that is developing. We have in this particular case study looked at a monofacial site, so not a bifacial site. In the monofacial site, it was the radiance and the back of module temperature in this particular location the most important. My assumption is that for bifacial, you would have to add the rear irradiance, and depending on the site, perhaps also soiling. But we have not studied this yet, so we'd be happy to learn in the future what the exact answer to this is. But this is my first thought, Greg.
Yes, thank you very much, Mr. Marc. The floor is yours, Mr. Greg, if you have anything to add. It's a pleasure to provide your participation with us today. The floor is yours, Mr. Greg.
No, I think thank you, Marc, for answering that. It's a great start that you've done, very exciting, and we look forward to further extensions and learning more.
Oh, thank you very much. Yes, thank you very much, Marc. I think if there is a question for other participants, if you have any question for Mr. Marc. So yes, there is another question for Mr. Munir Abraham. So Mr. Munir, thank you for your nice presentation. So the question is, can also is the following, can also be used for automatic quality control for irradiation data.
Yeah, this is a good question. Yeah, unfortunately, I have not looked into that yet, but I know there's already a lot of work done on automatic quality control in the BSRN collaboration. So I think more of quality control can be found there. But I think it can be interesting to see, what can AI do in quality control of data. Yeah. So I take it more as a suggestion. So I don't have the answer.
Yes, thank you very much. Thank you very much. So, Munir, feel free to make a contact with Marc for further discussion and further question. Thank you very much. So let's switch for the next presentation with Mr. Müller. Are you with us, Mr. Thore?
Yes, I am. Here I am. Hello.
Yeah, hello. Thank you very much for joining us in this workshop.
The pleasure is mine. I'm happy to start.
So let's start with a first presentation of Mr. Thore. So Mr. Thore holds a Master of Engineering in Sustainable Energy Supply from the RWTH Asian. Before founding PVRADAR Labs, he worked at the Research and Development Department of French Energy Gains NG in Chile and Belgium. Today, he develops PVRADAR. So PVRADAR is a software platform for transparent soil assessment from satellite data and seamless cleaning optimization for utility scale PV. So thank you very much again, Thore, for joining us today. The floor is yours. Thank you.
Yes. All right. I'm trying to share very well. All right. Here we go.
Yeah, it's okay. Yeah.
All right. Perfect.
Nice.
Well, then, thank you, everybody. Thank you for the invitation. Hello, welcome everybody to my talk. I will be talking about the title of my presentation is Physics-Based AI is Revolutionizing Soiling Estimation and Cleaning Optimization in Large-Scale PV. And we have had a few, well, my previous presentations have been mostly about questions during the operational phase of the power plants. What I would like to go into a little bit now is how can we use methods like AI, like machine learning, to predict conditions during the design phase of the power plant and prepare in the most optimal way to mitigate them, maybe as early as the design, and then be prepared to when they occur during operation. All right. Okay, so what I want to do is the presentation has 4 parts. First, I would like to give you a brief presentation about who we are and where we come from and what do we do. And then I would like to quickly describe the problem and better define the problem a little bit by explaining why it is important to assess soiling and optimize cleaning as early as day 1 of the design phase. And then I would like to show you how data, algorithms, and AI can help us solve these problems as early as day 1 of the design phase. And then finally, I will give you some examples from our work, some results from different conference presentations where we have also shared results. Okay, so with that, our motivation. So there have been reports, or there are reports, and maybe some of you in the audience that are operating PV power plants know that once a power plant is built, their performance is a little bit less than what was expected during the design phase. So in this report by PV Magazine and Kilowatt-hour Analytics for data in the US, they found that an average power plants are underperforming by 8%, which is a lot. And the problem is we're of the opinion that one of the problems is, or the big problem is that people or the project developers, when they are designing their power plants, they have they rely their estimations on input values for example, soiling, that do not have no very strong relation to the reality and the site conditions of their project. So what we want to do, or what we're doing at PVRADAR, is we empower project developers to achieve world-class performance and reliability across all climatic zones, transparently and traceably, and most importantly, we do it as you can do it that as early as the first day of the design, right? So what does that actually mean? We, in our activities, is separated into 3, or for now, we have 3 different fields or topics that we are interested in. The first one that I will be mostly talking about today is soiling risk assessment. So a project developer would like to know what kind of conditions they will face at a specific location when a new project is planned, to best prepare for it. Now, once the conditions are known, what we want to do, or what is needed, is to perform a cleaning cost optimization. That can be done very early to decide, for example, whether it makes sense to buy a tractor or to invest into a robotic cleaning system, or whether maybe manual cleaning is enough. And then there's a third topic that we're interested in, or that we're working on, that is the question of albedo improvement. Also a question that during design, especially in locations that are very dry and arid, it makes sense to consider those geotextiles or white plastic surfaces below bifacial modules that enhance the reflection of the ground and therefore yield additional energy and usually pay for themselves after just a few years. During my presentation today, I will be focusing mostly on soiling estimation and cleaning cost optimization. Right. So just in a nutshell, what can you expect when working with us? So the kind of results or deliverables that we provide, there is like linked to our first topic, the soiling risk estimation. What we do is we develop, or we deliver reports for a specific location. You can request a report for a new location that you're interested in. And basically what you get, you get a report that of course contains our methodology, the data that was used, the justification, but most importantly, you get 12 accurate monthly average numbers for the average soiling losses that you can expect at that location, and that you can then feed into your PV Syst to get a much better estimate of what kind of soiling you would have to expect at that location, instead of using maybe 2%, that is a standard value from PV Syst itself. Now, once you know what the kind of soiling problem is, you would like to do something about it, and then you can use our you can get a license for PVRADAR online, or PVRADAR platform, with which you can optimize the cleaning for that location, and therefore bring down the soiling losses and the 12-monthly soiling loss factors to a much lower level, but of course at the expense of cleaning. And there we make sure that this cleaning is as little as you need to, as little as possible, as cheap as possible. What you can also use this for is if, for example, you have a new power plant and you have to select a cleaning technology, maybe you want to buy a tractor, and there are many different offers, and it's very difficult to compare apples with apples. But our software helps to decide how much more, for example, would you be willing to for a cleaning technology that has a slightly higher cleaning efficiency, and how to compare this, a tractor maybe, against a cleaning robot that works very differently, and where the comparison is not that easy and you cannot just go by price. And then finally, what we're working on is during the, of course, soiling and cleaning are important during the operational phase as well. What we have there is we build software. Our tool enables the operating team to make decisions during the operation of the power plant based on forecasts. And this is where most of the AI comes in, based on forecasts of the soiling development, so that you can decide on which date is the most cost effective for the next cleaning. Before I go into the real presentation, we just quickly introduce us and the team. So this is the founding team of PVRADAR Labs. That's myself and colleague, former colleague and now partner, Franco Clandestino. We both have worked at big French energy companies. So we have been in the position of, well, our previous position, we were asked to support business units in making these kind of estimations and helping business units to build better power plants, build more cost-effective designs. And what we realized during the time is that very often the tools aren't there, and therefore we decided to build PVRADAR, and we teamed up with Konstantin Pogorov, a very capable software developer, and his team. And this is how, and together now we develop tools that really solve problems. We were founded in 2022. So far, we have had quite some success with a total of more than 50 projects analyzed for our customers, totaling or summing up to more than 4.5 gigawatts of plant capacity. And maybe just an interesting, we are a very international team. We speak a total of 7 languages amongst the 3 of us. All right. Now, the more technical part of the presentation. Why is it important to assess soiling and optimize cleaning during the design phase? And that I would like to explain with a little, comparison. So let's assume we are in the early design of a power plant, or what I would like to show is what can go wrong if you don't, and then of course what we can improve upon. So let's say we are a project developer working on a new project in Morocco, let's say, and unfortunately, for that very location, there are no measurements available, and also there's no time. Usually you have to make a bid, maybe you're participating in a tender, there's a deadline, you need to make a yield estimation, and for that you need to know what kind of soiling losses you would have to use. So there's no time to do the measurements, therefore you make a guess, and you could go with a 2% from PVSIFT or something else, and usually what people guess is something flat for the entire year. So a certain percentage, same in every month. And that might lead to underestimating of the production, but very often what happens is that people take a number that is too low, and therefore in the end, what happens, what I started my presentation with, the plant performs less well as it was expected beforehand. Right, then so that is during the very early design. Now let's say the power plant moves one step further, and we already are basing our expectations based on wrong assumptions. But now our EPC team needs to determine, create a cleaning or incorporate a cleaning strategy into the design. They may either think that the problem is that there is no problem. Therefore, a very small cleaning budget is being associated to the plant. And then people in operation later find it very difficult with a very small budget to maintain the high expected performance of the power plant. And that, of course, is a problem, because at that point, many of the options that you had during design, they're already gone. Alternatively, the EPC might also think that soiling is a very big problem, where in reality it is not. Happens less often, but may happen as well. In which case, there is a good cleaning strategy. Well, the intent is there to incorporate a cleaning technology into their designs, and then you would get quotes from many different cleaning providers and find out that prices are very different, and it would be difficult to make a decision. And you might turn out to just go for the cheapest one, because prices are of course easy to compare, but not necessarily for the most for the best quality, and that then can again leads to problems later on. So what is the solution? The solution is to incorporate data as early as possible, and then therefore be able to make data-driven decisions. Again, I know I repeat myself, but I cannot. It's something that I learned the hard way. It's important to start as early as possible to avoid very costly reiterations. Like the later design needs to be changed, the more costly it is. And once it's in operation, changes, even adding a cleaning system might be very difficult. And then, of course, once the power plant is being built, right, you have a good estimation, for example, provided by us. But then during the operations, you still want to measure soiling, you still want to have an open eye for it, and then fine-tune your cleaning strategy during operation that might still bring benefits. Okay, so how do we help our customers achieve this? So we do this with three different. Well, I already mentioned. So we have this. We have the soiling report that gives you the soiling loss factor, along with a very detailed documentation that you can then add to the project documentation, share with banks, share with shareholders, and it gives a lot of transparency and a lot of credibility to the project. We help with our software. It is possible to make a holistic techno-economic optimization of the cleaning strategy for that power plant, and to determine which technology is the best and also which cleaning frequency is the most cost efficient. And then the solution that we're building during the operation then helps to fine-tune that and really decide case by case, year by year. Okay, in this case, now it rained a little bit more than last year, so we will do the cleaning a little bit later, and that still gives a little bit of a benefit. All right. With that, let's jump into a little bit more of the theory behind and the underlying models. Or I would just go through the process of doing the soiling assessment and the cleaning optimization theoretically once, and then at the end I will show you some examples of results that came out. All right. So how can data, algorithms, and AI help us to solve this problem? Just to make sure that this is very well understood. Okay, so what is the theoretical problem? What we want to do is we would like to make a cost optimization in the end, to find the optimal cleaning strategy. And the optimal cleaning strategy is the kind and number of cleanings that brings down the total cost, which is the sum of the cleaning cost, of course, and the energy lost. If I clean every day, that is optimal in the sense that the power plant is never dirty, but of course that is might be way too expensive. Most likely it is. And then there's the other extreme where I clean never. That doesn't cost me much, but also there will be a lot of soiling losses. So the optimum is somewhere in between, and where exactly that optimum is depends on the soiling conditions, the meteorological conditions, irradiance, most and foremost, the PV plant technical design, of course, the market environment, at what energy sales price am I selling my energy? Then the parameters of the cleaning technology and the cleaning cost for the cleaning strategy that I have chosen. And in our software, one is able to input all of these inputs, and the rest, which one can't input, they are derived by our machine learning algorithms. Right. So how does it look like? What are the steps in our solution? So the first step, you would have to select the project location and define the design. Of course, depending on the location, if we're in the middle of a desert or in a more temperate place, soiling may be very different. For example, what we have seen in power plants in dry and arid, maybe, well, for example, in Morocco, I would assume this being the case, the soiling is there's a lot of mineral dust in the air, which means that the soiling does accumulate rapidly, but once there's a rain, a kind of gets rid of the soiling again, leaving the modules more or less clean. Whereas in places where you would not think of soiling as being one of the biggest problems in the first year, it happens that, for example, in Germany where I live, it happens that soiling builds up very slowly year after year. There's a layer of very sticky plant material building up on the modules that even though it rains, it never really goes away, and that is only, you can only clean it away with mechanical cleaning. And therefore, of course, and this is very well defined by the location, of course, and also the plant parameters, tilt angle, and so forth. Now then, for that location and for that technical design, we run a soiling estimation, and we do this with on the basis of historic data. So we go about and collect from different sources, meteorological data, the ambient temperature, wind speed and direction, humidity. Most importantly, we go and fetch 20 years of historic concentration for different components, particles, suspended in the air, for the very location. And also we fetch information about the rainfall that this region has seen. And all of this we combine in our soiling estimation model to get a historic soiling profile. I will show an example how that looks like at the end. With the soiling profile at hand, we can then compare, or once we know what the soiling problem is, we now would like to compare different cleaning technologies. So a user in our software has to select what are the different cleaning technologies that one would like to see in the comparison. And what we offer, or what the software is capable of simulating, is dry cleaning robots, dry and wet, cleaning tractors, also dry and wet. There's fully autonomous cleaning robots, manual cleaning. And all of these systems are described with their lifetime, the lifetime of different components. Of course, if you clean more, then of course your brush will be worn out sooner, and then you have to replace the brush. All of these costs, all of these implications are considered in our software. You need to have the cost, the operational parameters, and of course the cleaning performance, most importantly, the cleaning efficiency. We offer a database of available cleaning systems, but users are always able to fine-tune every single value if you think you have a better estimate, or just would like to find out what happens if the soiling cleaning efficiency was a little bit higher, a little bit lower. You can, and you immediately get the impact on the total cost of ownership of that system. What we're also experimenting with is including other mitigation strategies than cleaning. For example, anti-soiling coatings could also be modeled, but that is a feature that is still under development. But if you're interested, we can talk about that as well. Right. And now comes, so we have to find the system. We have to find the historic soiling conditions. We have to find what kind of cleaning is available to us. And now what we want to do is we want to make a forecast, a long-time forecast, 20 years into the future, to find out what will be the optimal cleaning strategy. And this is where machine learning techniques and AI come into play. And here, I don't have much time to go into detail, but there is basically two approaches where you have a data-driven approach in AI and a more physics or a model physics-based approach. And we're in favor of the latter, as we think that the AI is great in certain occasions, but still it is necessary to make sure that the outputs of that model suffice physical reasoning, and they are physically possible, and that we make sure with that approach. Finally, so again, where are we now? We have now our estimation of the soiling conditions in the future, and what we do now is we test for the different cleaning technologies, different cleaning packages that have been selected. We find out what is the optimal number of systems, what is the optimal number of cleanings, what is the optimal date at which it needs to be cleaned. And that, of course, can be different in every year. And the result is a total cost of ownership for each of the alternatives. You see in the bottom, you see the stacked bar plot. In red is the soiling cost. So even though you're cleaning, because you cannot clean every day, there will be still some residual soiling losses, which have a cost. And then in blue is the cost, the actual cost paid for the cleaning. And of course, you have to consider both. And we find in red, that is the scenario you do not clean, you never clean. We find that that is our base, that is our base case. And then in this case, in this example, there would be 3 systems that are better than never cleaning and 1 that is actually worse, more expensive than cleaning. Again, there will be an example. And I think, well, speaking of examples, now let's jump into some of the results. I lost track. Oh, I think I'm a little bit over time. Sorry for that. Well, yeah. So here's an example for a power plant in Portugal, where we combined. Where I think the results that you have seen before, they are from the power plant. So in this case, no cleaning, or what you can read from this is that for this power plant, the scenario of no cleaning is actually not the best one, and you would like to clean regularly. And the best that we have found was a wet cleaning tractor, 3 systems with an average 2 cleanings per year that would increase the levelized cost, the net present value of the project by 742,000 euros. Yeah, so a considerable or a nice improvement that you would like to take. These were results that we presented at the EU PVSec last year. I also have some results from the Middle East and North Africa Solar Conference, the MENA SC, where I presented this plot. This is a soiling profile for a power plant, I think in Oman. As you can see, based on the historic data, you see, the soiling conditions are not the same in every month of the year. In January and, well, between October and February, maybe they're a little bit lower, and then they increase, reaching their peak in August usually. But as we can see in the spread, every year is a little bit different. And that, of course, it makes sense to consider in your modeling. Otherwise, you would be cleaning at times where it's really not that necessary, and you should really put these resources in months that see more soiling. Finally, I can show you a comparison of different models and validation data. So we compared our prediction models with measurements for a site in Spain, and you can see, well, there's 4 different variations of well, we have different algorithms. We were experimenting a little bit with different algorithms, different models, and you can see that by tweaking the input parameters, and this is something done by the AI as well, or by our methods, by tweaking the input parameters of the model, we can have quite a good fit, not a perfect fit, but quite a good fit, and a much better fit than one would have guessed without any knowledge, which is unfortunately very often the case. And with that, I conclude my presentation. Please have my email here. If you have any questions, well, you can reach out to me or ask me now.
Yes, Mr. Thore, thank you very much for this nice presentation. Yes, it's a pleasure also to have you with us today. Let's switch for some question. Yes, okay. So let's start with the first one from Mohsin Rami. So Mohsin Rami asks you, do you think that solar panels with a special front layer can reduce soiling problems? Yes, Mr. Thore?
Yeah, well, it has been demonstrated that it works, right? So I do think, yes, they can. I think you would have to distinguish 2 main categories. One is the ones that are retrofitted. So I don't know, hydrophobic substances that are sprayed on the modules in regular intervals. And then there are other solutions that are applied during the production of during module manufacturing, which I think turn out to work a little bit better. Although I don't have all the data. What is important is that these layers, of course, are subject to the conditions on site. The more often you clean them, the more often they experience physical or mechanical cleaning, the faster they will go away. And this should be considered in your decision, into the question whether they make sense or not. So it's not, I do think they work, but whether they make economic sense depends on project.
Yes. Thank you very much for this nice answer. So let's switch for a second question. So the participants would like to thank you for your interesting presentation. So the question is about the cost-effective and saving of the application of coating for new PV plants.
Okay, and there was a little bit of lag in my audio. I understand there's a second question on anti-soiling coatings.
Yeah, let's repeat this question. So,
Please.
is your innovative solution more cost-effective in terms of OPEX saving when used and applied at a development stage of a power plant or a solar power plant already in operation?
Okay, very good question. Well, yeah, as I pointed out, yeah, I do think it is of course important to do both. You should never really just forget about the question at all. But the earlier you start, the better. So I would encourage everybody that is involved in the design of power plants to think about the question: how much soiling will this plant see, and try to get as much information about this as early as possible to build a better power plant. So the answer is clear: yes. It is important to consider during design, and then during operation, you follow up on that strategy.
Yeah, thank you very much. So the third questions, yeah, are there any precaution measures that we can take into consideration in the engineering design phase, avoid or reduce the soiling problem?
The question, I'm not sure to understand. Safety concerns.
The question about the precaution measure that we should take into consideration during the design of this anti-soiling coating.
But
yeah.
Very often soiling is a factor that you cannot really get rid of. As in, you might use it. You can apply. So if you want to build a plant in that area, you don't have a choice. You have to accept the soiling. So the kind of precaution that you can apply is make sure that your plant is. You take this into consideration by, for example, making sure that you have enough space between rows to have a cleaning tractor, buy the cleaning tractor, or even a cleaning robot that definitely needs to be installed and taken into consideration in the design, because otherwise the cost just explodes if you want to make a retrofit. Of course, if you have very local conditions, such as a road that isn't paved, you might consider paving that road to have less dust in the air, or building it on the other side of the street to have with the predominant wind direction is from one side. So there's things like this, but very often the location is given as well. So I think, yeah, precautions, and then you have to adapt your design accordingly, and that is mostly by incorporating a mitigation strategy. Another thing, of course, is you could just oversize your power plant a little bit more, and then have what otherwise would be clipping is now soiling loss. So in that sense, oversizing your power plant might also be considered a mitigation strategy, and at times might also be a valid strategy. I cannot hear you. You're muted.
Yeah. Sorry. Yeah. Well, thank you very much, Mr. Thore, for this nice presentation. It's a pleasure to have you today.
It was a pleasure. Please, if anybody would like to continue, reach out to me. I'm almost happy to discuss.
Thank you very much. Thank you very much. So let's switch for the last presentation with Mr. Catlin Mattheis. Mr. Mattheis.
Hey everyone, thanks for joining. Thanks for having me.
Thank you very much. Yeah. Thank you very much for joining us in this workshop. Thank you, Catlin. So let's start firstly with a presentation about Mr. Catlin. So Mr. Catlin has been working in the solar industry for 70 years. He began his career in the EPC side of the industry, working on some of the earliest C&I projects in the US. Mr. Catlin Mattheis is currently the CEO at Fracsun. He has developed sensors that are now monitoring solar losses in 27 countries across over 11 gigawatts of solar assets. So thank you very much, Mattheis, for joining us today. The floor is yours, please.
Okay, great. Yeah, thanks for having me again. let's see, am I able to share my screen?
Yeah.
Okay, great. So being the last one here, I won't, I don't have a very large presentation to go through with everyone, but I would like to do is potentially go through a bit of a live demo for something that really no one's seen in the world
Yeah.
yet.
Yeah.
We will be officially releasing this model in a couple months,
Yeah.
but I thought I would take the opportunity to kind of share here what we've been working on and what it's currently looking like. So for those that don't really know us or what we do, Fracsun builds a PV-based soiling loss monitoring system. We're currently deployed, as mentioned, over approximately 12 gigawatts in 27 countries now. That number changes all the time. And what we build and how it works is essentially a large area reference cell based soiling monitoring station. There was a question to accuracy earlier. Essentially, we use a PV device, one surface that is automatically cleaned every day, one surface that is collecting soiling loss along with the rest of the array. And we measure direct irradiance based on short circuit current using this model. It is referred to as method 2 in the IEC standard for soiling measurement. A couple features of this device is we do use matched PV cells. So what that means is essentially we light soak everything in our facility, and we test everything under a solar simulator. And any two cells that go into a single device are matched with the same electrical characteristics as each other. In this way, our focus is not necessarily hyper accurate measurement of irradiance, but a precise measurement of irradiance. So if you remember your high school physics with the bullseye, we're not focused on a wide grouping around the middle of the bullseye. We're focused on a very tight grouping, even if we are slightly off the bullseye, because all we care about in this case is the delta between the two. This device is also self-powered, it's self-communicating, so it can be deployed anywhere within an array field very simply without needing to connect to the SCADA system. I'm going to try to attempt to connect, to catch up to our time frame here a little bit, so I'm going to be a bit quicker. This is a wash extension. If you want automatic cleaning of the device itself, this is what we incorporate. If that is not desired, and say you have a team on site all the time that can manually clean the sensor, that is also an option. And I want to jump here actually to kind of a live demo of what our data portal looks like and how that data comes in. And if you go onto our website, you can get access to this particular demo portal. And I'm just going to do it live here. So one thing I like to start at the bottom here and show kind of what we're measuring directly. And what we measure directly is irradiance across these two surfaces, right? Over time, those two surfaces will collect material. The material is going to be removed automatically every day from one. And then we're going to measure instantaneous irradiance over the course of the day. Hey, there's a hand up. Feel free to interrupt me. I'm all about that. You're more than welcome to ask questions, and I will try to answer on the fly. I assume that will probably come in via the chat, so I'll keep an eye out for it. The important thing to note here is that when incident light hits the glass surface, the soiling represented or seen by the system is going to vary slightly depending on that incident angle. And there was the question about accuracy of sensors. One area in which optical sensors will always fall short is that representing what that soiling loss is, it can be a fixed amount of material, but if the angle of the sun is changing throughout the day, then you need to track how that light scattering is changing throughout the day as well. So we report here instantaneous loss. We're focused on a daily loss, but I'll explain why. Is that if you look here at the shoulders of a tracking system, during these parts of the day, the sun is the most normal to the array. I've also pulled in August, so it's late summer. And you'll notice that soiling loss indicated by the system is, in this case, about 7.5% on this particular day. But as we go to the middle of the day, where the sun is more oblique to the array, the soiling loss is going to be represented as a higher value. You need to capture this in order to really know what soiling loss is on a site, because we need to integrate this entire day. We need to weight this by irradiance, right? Because if you have 10% loss during one point of the day, and that's your highest radius point, then that's going to have a heavier weight on the system. So we integrate that over the course of the day, and then we come up to an insolation value, which this is what we're tracking. Daily sun hours is what some people call it. And this is going to be calculating the delta between these two. This is our clean irradiance versus our soiled irradiance. And then this is how we're going to calculate our daily loss for our soiling loss for the system. There's a question in here. I'm just going to pull it up. What do we got? Do I have any questions? Oh, that's you asking. Okay, so at the end of the day, we measure this delta across these two surfaces, and then we ultimately come to a total loss value for the day, and that is represented here. I'll mention this is an operating asset. It is a real field. This gets updated every single day, warts and all. And then you can see here, soiling loss will accumulate fairly linearly. To something that Thore mentioned, soiling rate is a very important consideration. In our portal here, we can highlight a specific area of this graph to calculate that rate automatically down here. And you'll notice that if you grab something kind of, let's see, I'm going to pull in a little more data. Let's go back to the spring. Okay, so if we pull in data from earlier in the year and we check that value, our soiling rate will be low in the early spring, late winter, as Thore showed with that, I believe it was Oman data. But then as we go beyond this point and we get later in the summer and the ground is drier, then as you would expect, if we highlight this section, our soiling rate is increasing. And this is going to change year by year, season by season. But as you go later and later, until we get that first rain, our soiling rate's growing, right? In this chart, we can also overlay precipitation. We can turn this into a line chart, and we can view all of our different soiling stations at this one particular site. So you can capture deltas across the site and all that. So what are we doing with this? That is what I want to talk about here. If I can reach my screen. And so what we're doing with that data is where the AI comes in, right? So we're collecting that data. It's coming through our portal. We can, on an anonymous basis, to some extent, we can share our customer data into a model, or we can share it as data reports, or whatever the case may be. So what we're currently working on is feeding all of our data into an AI model, as well as weather data, precipitation, of course, particulate matter data, O3 pollutants, nitrate levels, sulfate levels, as well as informing and teaching the AI on existing soiling loss models like the HSU and Kimber models, right? We have a lot of data on how these factors impact soiling loss from the model perspective, and I included that here. So the importance to the model and how it impacts it is shown, PM 2.5, as one would expect, is the largest contributor to soil loss, but PM 10 is a close second. And even O3 pollutants and nitrates and sulfates factor in. And these down here, even though they may be smaller contributors, these are things that cause cementation on plants. So when you see that soiling loss that's not removed by rain, that is persistent. And then finally, the model outputs. And what I wanted to show this group here, and I will yield my time shortly after this, is what that model is now showing is very, very interesting, because, like a lot of AI, it's very much a black box, but we feed all this information into it. We teach it what we can. your sessions expire, and what it puts out is really, really interesting. So this is our partnership with App Orchid, which we have developed this data product with, this new soiling model. And what they have is, this system is called Easy Answers. So what I can do currently now is I can go in here and you can ask this system simple verbal prompts, and it's going to look into all of our data. It's going to model that out. And what we end up with, once it takes its time, is, you know, some output. And let's look at what this is. So the model is currently bringing in precipitation, actual soiling loss, and I picked this location because this is the location of our demo plant. Currently, this is the only one I can pull in and show you guys, but it is working across the board with a little bit of tuning still needed. And like I mentioned, I think at the beginning, we'll officially release this in a couple months at the PVPMC workshop. But currently, and I can hide some of these values, so it's bringing in nitrogen dioxide, sulfur dioxide, PM temp data. I'm turning this off to make it a little easier to see. But here's what the model is currently producing. And you'll notice at first, which when I first looked at it, I was like, huh, there's a real problem here. But what the model is bringing in, and this green line is the actual soiling loss measured on the ground at this particular site, this location. But what our data includes, because this is an operational plant, is that this site is being cleaned, right? So you'll notice that all these drops in this green line of actual soiling loss measured at the ground correlate to cleaning events at the site where the site was mechanically cleaned. And so why is that good? Because this blue line, which now the AI model is spitting out and saying, this is what our soiling loss would be, is effectually a value of soiling loss if you were to never clean the plant, right? Which is great, because this is our starting point that we want, is we want to start at a point where no soiling or removal is being done to the data set. And, you know, then we can go beyond and use either our model or something like Thore's to then calculate optimal cleaning schedules based on this simulated value, and then come up with, you know, operational O&M budgets and get all that baked into a site or a project in the very, very early development stages. And, you know, first we can also say, what if I just want to know what the soiling loss was in Lemoore for in 2020? So currently this model is working. It's very handy, and we're just working to improve it before releasing here in a couple months. So I will yield time to catch us back on schedule, and, you know, reach it or let me know if you guys have any questions.
Yes, Catlin? You finished?
Yes, yeah. Sorry, I
Okay,
have to jump
okay,
pretty early, so I had to rewrite my
I was
my
managing a lot
presentation
of
here.
I was managing a lot of question. So you have a lot of question in your presentation. Yeah, I am managing this couple of questions. So let's start with the first questions. Yeah.
Sure. Let's see. Am I just reading about this?
Yeah.
Oh, I saw it,
Yeah.
and then it went away.
Yeah. Okay. Okay. Thank you very much, Mr. Catlin, for this nice presentation. So let's start with the first one. So the first one, thank you for your nice presentation. So how many arrays sensors do we need to optimize cleaning considering a large power plant above 1 gigawatt?
Yeah, this is a great question. We currently have 3 plants that we monitor that are about a gigawatt, around 800 to 900 megawatt. So we do have a lot of experience in this. The majority of people, because it's going to be a cost, benefit calculation for how many sensors deploy. Ideally, you might have 100, but is that going to make financial sense? Maybe not, and it'll be a lot of maintenance, et cetera. But the industry is currently kind of converging on what I would say is somewhere between one sensor per 20 to 30 megawatt in a utility scale environment.
Yeah, thank you very much. So let's switch for the second question from Mr. Fabian. In your solid losses integration, can you also account for a high clipping scenario where solid losses at high irradiance value are irrelevant?
That is a really good question, and also a very difficult thing for me to calculate on my end, and I'll explain why. So as you all probably know, system operators and owners and O&M groups, they're very cagey with their operational data. Security concerns are big as well. So in the US, we have something called NERC-FERC, where, a lot of getting data outside of the plant, excuse me, is very difficult. So more often than not, I am not aware of what the inverters are doing at the front surface of the glass, right? So the best way to model that is knowing a really high quality value for soiling loss, and then modeling that, in something post-processing that you're doing, as a way to track performance.
Yeah, thank you very much for this nice response. So we have also a question from Mr. Greg. So do you have a solar sensor deployed in Europe and or Africa or in the Middle East? What are your plans?
Let's see, Europe, Africa, and Middle East. So we do have sensors. About 15% of the sensors we have deployed are probably in Europe. A much smaller percentage, but non-zero in Africa. So we do have some sensors in Africa. And the Middle East, we do have quite a lot. Like I mentioned, those gigawatt projects, two of them are in the Middle East.
Yeah.
So yeah, some very interesting data. As far as, I'll take that answer a bit further and say the AI model itself for modeling these things and determining, on a region by region basis, initially will be released for the US. But as we have what I would call, a sufficient saturation of sensors within a given region or country market, we will start rolling out the model to two additional regions, and the Middle East will probably be second.
Okay. So we have also a couple of questions from Monir Ibrahim. So we have 4 questions. I will read all the questions for you, Catlin, at one. So the first one, have you compared the result of soil measurements based on manual and automatic cleaning of the reference cell? This is the first one. The second one, how can the effect of natural cleaning of large PV module be compared with that of PV cells? The third question, what is the source of the weather and irradiation data used by Fracsun? The last one, how can soil measured using cell current, ICC, with particularly circuit current, be used to estimate power loss of the power plant, of the PV plant?
Okay,
First question,
those
yeah.
5 questions in one.
Yeah, in one, yeah. I give you the all the question to provide us with a general response.
Okay, so as far as cleaning events, so when rain occurs, we can see that sometimes, rain does not clean entirely and bring the plant to zero. So there is a threshold that as you measure, you learn more and more about that threshold. Differences between automatic and manual cleaning, I believe that is in reference to the data quality in our sensor. And what I will say to that is essentially your granularity of data is going to be determined by how often you clean. So if you're not using that automated cleaning system that we do supply, then and if you clean once a week, then you're really only getting a weekly soiling loss value. So that's kind of the major difference. I'm sorry, I have ADD bad enough that I'm 2 out of 5 is not bad. What did I miss? Oh, you're on mute. You're on mute.
Yeah. The third question, what is the source of weather and irradiance data used by Fracsun?
Yes. So currently for the US, we're pulling in data from NOAA as well as satellite data for weather. In our portal page, we pull from a weather API that is based on location nearest to the sensors that are deployed.
Yeah. Thank you, Mr. Catlin, for this nice response. So, Mr. Munir Ibrahim, you could directly contact Mr. Catlin for further discussion and explanation. Thank you very much, Mr. Catlin. This is the last presentation. So let's switch for all the speakers. If you could activate your camera for a little bit small discussions. Yeah. So thank you very much. Thank you very much, Fabian. Thank you very much, Catlin. Thank you, Marc. Thank you very much. So for the others, if you have any questions. So I have heard some question for Marc. Is a missing question for Mr. Marc. So Mr. Marc, in your experience, which soil sensor are the most accurate, optical or electrical based?
Can you hear me?
Yeah.
Yes. That is a good question. And in my experience in soiling, it is less about the sensor because both these sensors can be accurate. It is much more about the variation in the site. So if you look at a single module, or if you look at a string of modules, there, in my experience, the uncertainty contribution in the measurements, it's much more from the variation over the site and less from the actual measurement principle that is being applied.
Yes, Marc, thank you very much. Thank you very much for this response. So Fabian, if you have anything to add?
Yeah, I would suggest so, because even the distribution of soiling plays a big role here, because you induce mismatch effects, like from a certain point of amount of soiling, of course. And then you also have to consider that mounting a soiling sensor next to some kind of module, then these surfaces tend to behave differently in terms of soiling. So you really need to integrate those sensors well into your power plant, into your normal solar array,
Yeah.
So that behaves similarly. So putting them next to the soiling, to the modules, as in Fracsun's or your case, Marc, then that's the way to go. Of course, to have the same surface, basically, that behaves similarly.
Yeah. Yes, Fabian, thank you very much. Mr. Thore, thank you very much for joining us today and providing us with your presentation. If you have anything to add.
Well, my camera seems to stop working. Well, I hope you can hear me. Yeah, so
Yeah.
I would say that if I had to choose between optical and electrical measurements at the same cost, and they are both easy to install, I think I would go for electrical measurements as they're closer to what I'm interested in. I mean, in the end, I'm interested in the effect of soiling on the production of the power plant. If I can measure this based on actual output of a single module, I think I will be closer to what I actually want to know. But of course, I think the biggest problem with soiling measurements today is not necessarily the way it's measured, but more the way it's maintained. And I think maybe Marc and Catlin can agree that mostly it's like it doesn't really matter what soiling system you install if you not properly maintain it. And so the most important thing would be that it's maintenance free or needs as little maintenance as possible, because the human factor is usually the problem. And having the the clean reference not actually clean is probably a much higher contributor to error than the way of measuring is. So there's a benefit, and both systems that have been presented are very low maintenance or no maintenance, so that is a big plus, of course.
Thank you very much. Yes, yeah, we have also in animation my colleague Sharaf. If you have anything, Mr. Sharaf, to add.
Thank you, dear Abdulatif. So I would like also to thank all the speakers for this interesting presentation, as well for your support in this workshop. So thank you so much for this interesting presentation showing the recent advance in the different fields related to the application of AI in the field of photovoltaic and CSP plants.
Yeah.
Maybe there is a question for Greg now. From Greg, yeah, to Marc and Catlin and all presenters, across calibration, validation, and comparison of the all models. What are the chances and opportunities to apply the models and approaches to the same data set? This is because different models and AI approach may result in different conclusion. So I don't know if Marc and Catlin can read the message from Greg.
Yeah, Greg, maybe if you could clarify that question a little bit. Are you saying to feed different data sets into the same AI, or to feed the same model into different AIs in order to cross-pollinate?
The second. So in other words, you've got one data set or several data sets, data set 1, 2, 3, 4, and I can see maybe what you get. Thank you for showing that advanced. I can see what the other presenters have shown, but I don't know which one is right, or if there's variation between the two. So let's just take one data set and see what each one of the AI models would predict for certain parameters. Does that make sense?
Yes. And
of course,
I would propose
you guys would have to collaborate in such a way that has never been done before, but we could ignore that for a moment.
The likes of which the world has never seen. Yes, and I think this is something that the PVPMC workshop is very good at, and Sandia National Labs is setting up I guess it's kind of like a competition where everyone will take the same data set. They will model an operational asset, and then everyone will compare notes at the end to see, what went right and what went wrong. Yeah, we would be definitely interested in doing that.
Tell the participants here where they could learn more about that effort.
The PV performance. Oh my gosh, I'm gonna mess it up. PVPMC, Performance Modeling Collective or Collaborative. I would just Google PVPMC. There are several workshops throughout the year that focus primarily on improving modeling efforts of PV assets. Yeah.
I can highly recommend. And I was at the PVPMC in October in Italy, or sorry, Switzerland, close to Italy, and I can really recommend the conference. It's all about modeling. In my slides, there was one slide on comparing satellite data to ground data, and there I used some NREL data. So NREL puts online some data sets with a lot of sensors and the PV test PV plant output, not a real life plant, but a test plant. So I can recommend that also to people that are interested in testing their AI on real data.
Yeah. And to add to that, Greg, also is we're currently validating our model against ground-based measurements to ensure that the model will produce a very similar result as to where we're actually measuring all over the country and world. And then that's going to go through a validation process with, you know, one of the big three, Black & Veatch or one of those types.
So thank you, Greg, for this intervention, and thank you, Marc, Mattheis, Fabian, for the answer, and as well for the comments about this intervention. So before closing this workshop, I
Yes,
will. So
yes,
we,
Mr.
You can see my.
Yeah.
My laptop.
Yes, Sharaf.
Thank you. So today we mourn the loss of our friend Zakaria Al-Mazouzi, who passed away last year. As we reflect on his life and the impact he had on each of us, it is so difficult to find the right words to express the depth of our sorrow and magnitude of our loss. However, amidst our grief, we find solace and the memories he gifted us. May his soul sleep in peace, knowing he will forever remain in our hearts, cherished and remembered.
So thank you very much, Mr. Sharaf.
Thank
Yes,
you.
I would like also, I would like also to give a special recognition Professor Greg for his invaluable presence and for generosity sharing his data and material in the chat. So, Mr. Greg, your support has been instrumental in enhancing the learning experience for all involved. Rest assured, we will ensure that the valuable information is shared with students, fostering the continued interest and development in this area. Thank you very much, Mr. Greg.
Thank you for organizing this.
Yeah, thank you very much. So before closing this workshop, let's yeah. So before closing this workshop, let's also thanks the advisory teams for gathering all such experts in the field of solar energy and artificial intelligence. Let's start with my colleague Ala Azouzout, Musab Lidrisi, Sharaf Hajjaj, Mohammed Azroual, Hussein Zitouni. My colleagues, if you have anything to add.
So thank you so much, Dr. Abdeltaif. No special thanks to add. I would also thanks to all the participants and let them know that we will share the different information about this workshop in our website as well in LinkedIn, Facebook, as well the other social platform. And again, thank you so much for our speakers for the support to be with us in this workshop, and hope to see him in our next
event.
Yeah, in our next events and workshop. Thank you.
So thank you very much. Thank you, Marc. Thank you, Fabian. Thank you, Catlin. Thank you, Mohammed. And thank you, Thore. Thank you very much for all your contribution and all your efforts.
Well, a
Have
pleasure.
a good day, everybody.
Thank you.
Thank you.
Okay, thank you very much for all participants for joining us today.
Thank you.
Bye, everyone.
Okay, bye-bye. Thank you very much.
Goodbye. Bye-bye.
Bye.
Goodbye. Thank you.